So questions 2 through 5 were multiple choice questions, and before I jump into those, I want to review some of the key differences between linear functions and exponential functions. If I'm sitting in GeoGebra and I type, for example, y equals mx, and I might want to hit m times x and then plus b down in the input bar, GeoGebra recognizes that two of those things are variables, x and y, and it knows that those x will vary, and as x varies, y will change to adjust it. The other two things there we call parameters, m and b, and once we select values for m and b, that y equals mx plus b describes a particular line. Now GeoGebra says, would you like to create sliders for m and b? And I'll just say yes, create sliders. And what that does is it allows me to conveniently change the value of m and b to get different lines. So if I put my cursor right, I actually have to grab this move tool. If I put my cursor right here, I can grab this and I can, that's just the label for it, but I can grab b and I can change b. I can make b larger. So you can see when I bring b right there at 3, I've got a y-intercept at 3. I can bring this up and create a y-intercept at around 4, and then I can bring it all the way up to a y-intercept of 5. And this value is the slope. It's this rise over run pattern, and I can change that too. Right now it's currently set at 1, and if you look at the equation, it's y equals 1x plus 5. That 1 corresponds to this slope pattern we see. I have a rise of 1, a run of 1, right? Up 1 over 1. And I can see that repeating throughout this entire function. Anytime you want to, I could grab this move and move the view around to take a look at it in different places, but you can definitely see this up 1 over 1 pattern. Now if I bring this over, I can change the value of my slope. For example, I could bring it and I could change it to make it the number 2, and whoops, I can make it the number 3 also, but I'll make it 3. So at this point now you can see that I've got this slope pattern where I'm going up 1, 2, 3 units and over 1, right? So again, these two parameters, slope and y-intercept, describe a particular line. And once I have this particular line, what varies is x and y. As I select different x values, this function, 3x plus 5, tells me the y value that goes with it. So if we just look at a couple values down here on the, for example, on the x-axis, you can see when x is -1, this relationship tells me how do I find the y value that goes with that. And it says you multiply the -1 times 3, which would give me -3, and then add 5. So when x is -1, you can see that y equals 3. So this is the point right here that is on that graph. It's y, x is -1, y is 2 actually. I said 3, I meant 2. So again, we see here how changing the parameters creates a totally different graph, and then once those parameters are locked in place, right now we are talking about a particular line, and we can view and observe things about the particular line. This one now has a y-intercept of 3, and it still has a slope of 3. So that's a linear situation, right? Now let's take a look at an exponential function. So here we're looking at y equals a, and then we've been multiplying times b and then raising that to the x power. Now as soon as I enter that, it's asking, oh, I notice that you have that's interesting. It says create sliders for b only. It didn't ask me about a. I feel like I have to be a little bit more explicit and tell it y equals a and then go times b to the x power. Now it sees that there's both a and b, and it's going to create sliders for each of them. So what I've done is I've moved the location of my two sliders, and I also created things that are called, these are linked input boxes. So if I type a value in either one of these boxes, it'll change these sliders exactly. Currently you can see my multiplier b is the number 1, and my y, my starting value, right, the 0th term is 1 also. So you can see it's starting right here when x is 0, it's hitting 1, and then it's continuing to multiply 1 times another 1 times, so it's not growing or decaying at all. I can come in here, I can say, look, I want it to start actually at a value of 4, and I can also say that I want it to, every single time it increases by 1, I want it to double in size. So as soon as I do that, you can see I've got this function that's showing this growth, and I can zoom out to see it a bit more. But the function right here is y, f of x, or y, equals 4 times 2 to the x power. You can see when x is 0, this becomes the number 1, 2 to the 0 power is 1, and 1 times 4 is just 4. So when x is 0, y is 4. When x is 1, which is in between these two, you can see it goes up to 8. And when x is 2, this should cross up here at 16. And you can see there, oops, way up here is, oops, way up here is that point. This point right here is about 216. So I can go through and change these values and totally change the characteristics of this function. I can give it different multipliers, and I can also give it different starting values. In fact, the starting values, it doesn't look like it would like them being negative, so I'm going to keep them positive. But also, you know, our multiplier is what we're growing by. So if I'm told something is growing at a rate of, let's see, 5% per year, if I know that I have a 5% growth, I would take 1 and add to that 0.05, so get 1 plus 0.05 or 1.05, and that's what 5% growth looks like. And right now it looks kind of insignificant, but if you zoom out and give it more time, 5% growth looks pretty impressive at a certain point, because, well, it's just the fact that it's just continuing to grow. So you can see it takes off there. I'm going like 90 or 100. I don't know what these units of time are, but 100 years out, or 100 days, or if we're talking about bacteria growth or something. And if I have something that's decreasing in time, let's say that I have, say that I'm starting with 6, and it's decreasing by, let's say it's decreasing by 3% per year. Maybe it's 6,000 people are in a town that's getting smaller. So I can put my initial value here at 6, and these are representing thousands of people. I forgot that the slider only can hit 5, so we'll use 5. So it's starting at 5, and then if I have a 5% decrease, what I do is I take my multiplier, and instead of adding the 5, I would take 1 and subtract 5 from it. So my multiplier would be 0.95. So what we're looking at here is now a 5% decrease per year, and we are starting at 6, but every single time we move out, we're multiplying by 0.95. Only 95% remains, and it's decreasing over time. So again, in general, if you look at it, this value right here is our 0th term, or where we're starting, and this value is what we're multiplying by. If this number is, if you recall, if it's between greater than 0 but less than 1, if it's in that range, it's representing decrease. If it's greater than 1, it's representing an increase. And if it's equal to 1, it's totally static. If I come in here and I change this number to 1, I end up getting just this horizontal line. Right? Nothing's changing because I'm multiplying by 1 each time. So if we think about that stuff in context of questions 2 through 5, question 2 said, which exponential function has an initial value of 4? Well, first of all, the key word here is an exponential function. This is a linear function. It's a line, so it clearly can't be choice A, because that's not an exponential function. B is exponential, C is exponential, and D is exponential. Has an initial value of 4. This one has a multiplier of 4. This one has an initial value of 4. You can see it starts at 4 and it's increasing by 20%. That's why our multiplier is 1.2. So C is the correct answer here. We have an initial value of 4 and this is an exponential function. Question 3 says, which exponential function has a multiplier of 0.92? C is not exponential, that's a linear function. D is just it's a constant, right? F of x is always 0.92. That's not a it's not an exponential function. That's just a straight line. For B, you can see our multiplier here is the number 3. We're not looking for that. We're looking for a multiplier of 0.92. It does have an initial value of 0.92, but that's not what we're looking for either. We're looking for a multiplier of 0.92. So that's choice A. Choice A has a multiplier of 0.92 and an initial value of 10. What kind of graph does an exponential function have? Well, most of them, with the exception of when a times b to the x, when b is 1, most of them are curves. And then finally, where does the graph of the function f of x equals 15 times 3 to the x cross the x-axis? Well, one of the things that we know is whenever we're crossing the x-axis, no, it says crossing the y-axis. When we are crossing this axis, the y-axis, x always equals 0, right? At this point, we know x is 0. So if I want to know when I'm crossing the y-axis, I could simply put the value 0 in for x. And 3 to the 0 power, of course, is 1. So I'm looking at 15 times 1, or 15. So this is crossing the x-axis at 15, which was choice A. So those are the 4 multiple choice questions that appeared on the test.